Right, we are back. Good afternoon, everyone. Welcome back. Hi, Dominika.
Okay, okay, I'm sharing.
I'm
Second now.
Okay.
Okay. Okay, so I'm going to slideshow from the beginning. So I hope everyone sees it. If not, okay, great. So first disclaimer.
I'll just introduce you for a little
Oh,
bit.
great. Go ahead.
My name is Marzia Miletto, and I'm one of the microscopists at the Pacific Northwest Center for CryoEM. And I would like to introduce today's last speaker, Dominika Borek. Dominika works at the Biophysics and Biochemistry Department at the University of Texas, Southwestern. And the title of her talk is From Map to Model, Practical Approaches to Low-Resolution Cryo-EM Model Building and Validation. And please give a warm virtual welcome to Dominika and take it away.
Great, thank you very much for the introduction. So basically, I changed a little my talk based on what other people were talking about. At the end, I plan to show you how to refine the structure using CUT and one of my examples. But first, disclaimer, I'm co-founder of the company which develops software for cryo-EM, so I have conflict of interest. So everyone who knows me knows that I love those three quotations. So in theory, there is no difference between theory and practice, but in practice there is. It doesn't matter what basically happened to the cat as long as it catches the mice. And there are known unknowns. I promise you that they will be relevant to this talk. So first, what is the resolution model building? So you get the map and you want to get the model. In this case, basically, I'm showing this as this cartoon. I don't think that we even have agreement during this short meeting about what low resolution is, because for some people, low resolution would be 2.5 angstroms, where you start being a little uncomfortable about some loops or maybe some connections. Map looks fluffy locally because locally it's not 2.5 angstroms. And for other people, low resolution is 6 angstroms. So I will be talking a lot about secondary and structure elements, because to some extent those secondary structure elements define what we can actually see at which resolution. So you can see alpha
Dominika,
Yes.
If I can interrupt real quick, it looks like you might be sharing the wrong window. We're just seeing the title slide in PowerPoint.
Okay, let me actually see. Application window. What do you see now?
There we go. That's perfect.
Okay, we are still on second slide, so don't worry.
Thank you.
Okay, so basically, let me actually come back to this. So at the low resolution, you can see actually helices at very low resolution. So all membrane protein people are happy. You can see DNA stacking at so-so resolution. So DNA people might be partially happy. They know that they have DNA, but unless they have additional information, they may not sequence. With beta structures, you kind of 3.9 is where you actually start having problems because you cannot separate those strands. Where I'm going with it. So for me, low resolution is a kind of around less than 3.5, but more than 4.2. Because around 4.2, I genuinely think that we are start more docking and relying on the AlphaFold models without any refinement other than semi-rigid body, versus basically below 4.2, where I can attempt at least some type of refinement. And it may be, okay, let's actually see whether I can change. Here we are. So while we have actually the problem, so that type of problems which we deal with during the model building are called inverse problems. So it's very easy to take all atom positions and calculate either electron density map in X-ray crystallography or some, maybe it's not easy to calculate, but you can calculate based on the equation. This is called forward problems. But when we have a bunch of data, here I'm showing the particles or even reconstruction map, we basically are answering questions: what is the structure with which caused this map look like that? And in contrast to the forward problems, where you can calculate, in case of inverse problems, they have specific features. And you see that here, these features very well overlap with the cryo-EM model building problems. The first feature, which is quite common, is ill-posedness, which means that solution may not exist. This is more crystallographers. They basically may have the fraction, may not be able to basically get the solution. In case of cryo-EM, if you have map which looks like it has secondary structures, you kind of have solution, but it doesn't mean that you will be able to build model which is reasonable into it. Moreover, the second feature is that the model may not be unique. So you may have situation, particularly at low resolution, that the same sequence or locally the same sequence will agree with the map almost in the same way. This is not uncommon. At low resolution, registry errors still happen. Sometimes for someone who is more experienced, it's easy to fix those registry errors, but frequently happen that even experienced people have problems. So, and in addition, the calculations or basically the interpretation may not be stable. So those problems are also sensitive to the instability and noise, which means that even small changes in the process can cause very different results. And anyone who actually dealt with the reconstruction knows how sensitive the reconstruction is for the cleaning of the data. And there is need for regularization. What does it mean? You have to provide some additional knowledge. And I'm going to argue over and over in this talk that for low resolution model building, the prior is incredibly important. And this was coming back many times during this talk. What should I do? Should I fit better to the density or fit in such a way that geometry agrees with the chemistry? So the answer to this question here is that actually it's not that strong and uncommon opinion. You absolutely should go with the chemistry. There is no reason that your 5-angstrom structure has unusual bond lengths, unusual angles, unusual features. Even if it has unusual features, you would have to have data to support it, and low resolution data will not support it. So let's go back to the chemistry. So coming back to the prior knowledge, and actually you hear very often in the context of cryo-EM and X-ray crystallography that basically how to incorporate prior knowledge. Usually we use for that some type of Bayesian reasoning. It's not always called Bayesian reasoning, but at the end, we are incorporating prior knowledge using that type of framework. So quick introduction, what it means. It means that you always look at things in the context. So what worked for your friend doesn't have to work for you. There are some common features. Here you have basically quick introduction. You are in the park on September 30th, which is obviously important here. You see this person running towards you. What do? ChatGPT suggests that you have to run away. You should call for help immediately, find safe place, make noise and draw attention if people are around. If you just change the date and see the same situation on October 31st, what do? You actually check, according to ChatGPT, but also according to common sense, you shouldn't panic because it's Halloween, so it's very possible that this is just dress up. You should smile, wave, and compliment the costume. So what kind of priors we have in model building and how we should handle them? We have priors such as chemistry, bond lengths, interactions types, and their energies. Libraries incorporated in the model building software handle it very well. We have macromolecular structure patterns, so primary, secondary, tertiary, and quaternary structures. This is relatively well incorporated in the software, but not very well. I will mention later where I suffer as a model building person. And there is evolutionary and structural conservations. And this is, again, not very well incorporated in model building software, but there are tools. I frequently use a tool which is called Conserve. I basically give here a link to it. And the reason is not that I cannot handle conservation myself, but Conserve has a very nice feature, which is important when we have so many genomes, that it handles all the sequence comparisons for me. So I don't have to worry about basically selecting out of 2,000 sequences the ones which actually provide the most information. So here we also see that if we are dealing with low to high resolution, basically we should trust maps, experimental maps at high resolution, and we should rely on geometry, again, opinion, but really not that controversial at low resolution. So I know that it sounds like I'm introducing here, again, the basic biochemistry, but we frequently forgot about some features of the structural elements. So when you build the model, you hear about alpha helices, which I'm listing here, and the standard beta strands, which I'm listing here too. But there are other structural elements, and at low resolution, this is where usually there is the most of uncertainty, which leads to the registry errors. Let me actually see. We also are basically well aware of the standard interactions, such as covalent bond and hydrogen bonds, but more basically the ones which are rare. Pi is not that rare, but some of the interactions which are actually acceptable and happen in proteins, they are not that discussed, at least not in a standard environment where the model builder is learning how to build the model. So here I'm providing few which you should consider, and when you see them, why you should consider them, because they tell you that you build the model correctly if you see such interaction. And in particular, if we have thousands or residues of protein or nucleic acid, and those interactions which we expect to see appear in large groups, we know that the registry error don't happen, and basically didn't happen for us, and that model is more or less correct. I'm not talking yet about indicators of correctness. And I provide also, this is, by the way, excellent paper, I provide also expected frequencies. So in the protein structures, I don't know them for RNA, but just so you know that basically these are common interactions and you should see it. And even more, you should not try to remove them, because some of them are so unknown, so much unknown, that people try to basically rebuild models to remove. In particular, CHO hydrogen bonds are not that broadly discussed. So what is the first structure which usually gives people a little problems? So when you have a helix, I drew here, basically there is helix here on the right. In this helix, I remove all the side chains and just left the top, so it's clear what I'm talking about. The helix has partially positive charge here, and this partially positive charge has to be balanced, and it's balanced by so-called end cap. Those end caps have very specific structures, and one of the things which is frequently problematic at low resolution is how this end cap is built. So basically, it happens quite often that it's built incorrectly. So that's the first place which I would check after other checks, which I will show at the end. Another, even worse place where you should spend a lot of time are C-caps. So the other end of the helix has the same thing, a little of charge, which you have to basically properly close. And there are many types of the C-caps. At low resolution, actually at any resolution, but at low resolution, this is a problem. Many helices have more than one C-cap. So you have mixture of two or sometimes even more than two. So at low resolution, this mixture generates a lot of problems my experience is that this is where the most registry error originate. So I would basically really inspect if you are working with the alpha helical protein rich in alpha helices, both C caps and N caps. Now coming back to this resolution, here we see two types of beta strands connected to each other with the hydrogen bonds, which I didn't draw. So this is the first problem with the low resolution model building. If you have alpha helical protein, you can actually go to, I would say, 4 angstroms, you can build decent models. And we saw many basically we saw many examples yesterday of such model building. But with beta stranded proteins, you really need about better than 3.9 to actually be able to separate beta strands. Otherwise, you start seeing densities which actually don't look like beta strands at all. So what you can do, you can dock, and you can basically just treat such structure as a rigid body. There were many tools shown already yesterday and today. And basically focus on the parts of the structure which you can model basically at the atomic level. But honestly, I would not attempt, if you cannot separate beta strands, I would not attempt to treat them as a, basically I would not attempt atomic refinement. This is most common non-alpha helix and non-beta structure, which by the way is not stabilized by hydrogen bonds. Again, I removed side chain, so it's easier to see that this is extended structure. So frequently when people talk about unstructured regions, you know that structured region means different things for different people, the same like resolution. Unstructured doesn't mean that it will not have structure in the cryo-EM reconstruction. For some people, unstructured means that it's not beta strand or alpha helix. Many regions which don't have alpha helical or beta stranded structure, they still are perfectly ordered in the structure because they interact with other elements or structural elements. So this is, for instance, one of the very common so-called random coils, which actually is present in many structures in PDB. This classification was done by my colleagues Zbyszek Otwinowski many years ago, and already this structure was one of the 20 most represented. And it's relatively long, and it happens because my guess it's probably present in one of the common enzymatic folds. Another thing which you should pay attention to, so we have Ramachandran plot, again, many talks. However, the basically Ramachandran plot position of given residue really depends on the environment. So there were, again, many people who are working, but you may, depending on what kind of training you got, you may not be aware that there are potentials, which are, by the way, implemented in the software, where actually there is basically taken into account neighbor dependent probability of Ramachandran distribution, and neighbor means both the residue before and after. So here we see one residue, glutamine. I copied this from the paper by Roland Danbrack. So his group basically is recognized for work in this area. And if you are interested in some non-alpha helical and non-beta stranded structures and would like to basically check if your low resolution fragment perhaps is described in those libraries, you may basically research his webpage, which I also provided here. By the way, MolProBT also has such the backbone dependent and neighbor dependent libraries. My point is rather that at low resolution, there is no way that you will get fully automatic build model. You almost always have to rebuild something locally. So being aware that there are those tools, this can help you to actually check whether these interactions which you try to build really were observed before or are probable. But even if you build model automatically, you still will have to inspect it. So still knowing that there are these dependencies is really helpful. So here, coming back to our glutamine, here we see the Ramachandran plot for glutamine, and it's not divided. So basically whatever residue is after glutamine all together shown. On the right, we see actually the glutamine and how this Ramachandran plot here starts being decomposed depending on the neighbor. So obviously the neighbors such as proline and glycine are the most interesting because these are the weirdest amino acids. So in case of proline, we see that basically this peak, which was very prominent on here, is almost non-existent. So for the, let me find glycine. Oops, of course. I did basically, I see you here. Okay, where is my glycine? Okay, lysine, glycine. Huh? Okay, I don't see glycine. It could be that it was on another figure. Oh no, it's here. Glycine is here, sorry. So when we see the glycine has basically also a little smaller peak, which is basically related to some being in the middle of the alpha helix. So anyway, next factor which you need to remember about when you are actually building at low resolution are scattering factors. So in particular, if you are coming from X-rays, in X-rays, I just basically draw the most annoying part for me personally. In X-rays, you have very nice dependence on the atomic number, specifically because oxygen is heavier than carbon, you actually see more electron density for oxygen. This is not true for the cryo-EM maps. This is actually taken from the paper by Mark Yeager group. In electron density maps, oxygen heavier. In the maps of the potential in cryo-EM, carbon is heavier. And our eyes have problems with it. In addition, as you can see, there is dependence on the charge, which obviously is present in all the structures. At a low resolution, we may not be able to model it, but we still see the differences in the shape of the map. So take it into account. This is also the reason why the water is not that well visible or not well visible for us and requires a little sharpening if you want to build it, and a little more reliance on the prior knowledge. We actually know for many, many positions where to expect the water. Anyway, you shouldn't build the water at 3.5 angstrom map probably anyway. So another one, and here is the only way, only point when I actually mention experiment. So what you see here is one of our benchmark proteins, which was reconstructed. So we collected movies, like everybody is collecting, and then reconstructed after performing reconstructions on the properly weighted movies. We actually also went back and reconstructed from the first frame. I think that this was 25th frame, basically a little farther and kind of at the end. So in the parentheses, I'm showing the doses. For people who don't operate in the dose world, basically on the first frame, we already had the dose which crystallographers consider significant. Here at 0. This was Talos data collection, by the way. Here, on this frame, we already are losing resolution a lot. Here, basically, we still see the structure. I, on purpose, put this helical, and not surprisingly, there is no structure here. So one of the things which you will hear frequently is that the magic software will take care of it and properly upweight the beginning of the movie and properly downweight the end. This is absolutely true. The problem is that if you fractionate your movie in such a way that you dump here 8 or 12 megagrays, which some people do, I'm not going to name the names, then there is nothing to recover. Software is not going magically get the signal which was already lost. So it's much easier to fractionate with the Falcon camera, and PNCC is one of many places which every time when I collect the data, they hear that I absolutely don't want to exceed this dose per frame if this is K3. But what I'm trying to say is that a lot of things which you see in MAP can be, unfortunately, a result of radiation damage, because even with this upweighting, we still lose signal and there are still specific changes. So here we see those specific changes. The green map represents the part. So the blue map is the map which is averaged across all frames, and the green maps represent the signal which we would have at the beginning. So this is the radiation zero dose extrapolated map. So this fragment shows you that we lose the signal on methionines, 2 of them. Not much. You can still build sidechain here, no worries about it, but you can very clearly see that this blue density is weaker than the green density, which I'm showing here. And by the way, this is not the worst case. This is actually relatively high resolution. On the right, we see very clearly the carboxylation. And you can see that this blue density would basically, it's more difficult to build the end of this side chain if there is the carboxylation. Here, we see that basically there is loss also. It's actually not uncommon. There is entire chemistry behind it, which I'm not discussing. There is hydrogen bond here. So between this carboxylic acid and the lysine. So after this bond is lost, likely because of the decarboxylation, this thing is not necessarily damaged, but it gets a lot of flexibility because it's not bonded anyway. So what you see is the blue map. What basically first frame has, if you collected data correctly, is the green plus blue. So you want to, so I will come back to this later, I have wishes. Then there was a lot of questions about, should I build sidechains? You should absolutely build sidechains, even if you are uncertain. And there are several reasons for that, which were very well described by basically Pavel gave very nice answer why you should do this. But I would like to focus on the B factors, because people frequently are like asking, oh, should I let the B factors go up? So B factors, which is this isotropic or anisotropic for high resolution structures displacement of the atom, actually describes uncertainty very well. And in cryo-EM is actually used as a, to some extent, as a uncertainty measure, not to some extent, it is used as an uncertainty measure, which actually captures a lot of factors, not only vibrations of the atom. Nevertheless, people imagine that high B factor means that atom is everywhere. It's actually not true. So we know exactly how far it is based on this very nice equation. And even for very high B factors, your atom is not everywhere. It's actually within 200, which is happening often. It's 1.6. 500 is 2.6. So modeling the sidechain in the most, basically as a non-clashing good conformer is actually way to go. But there is another factor which I consider as a reviewer of the structures or consumer of the structures. A lot of people cut the sidechains because they don't know how to model them, of course. But as a consequence, their validation statistics are better and they reflect something which does not have place. Specifically, clash score will become better if you remove a lot of sidechains. So that's another thing, that basically, if you treat clash score as some kind of problem, and there is fully expected that clash score will be higher if you have lower resolution, then just optimizing it by cutting sidechains you will optimize clash score, but it will give like false confidence in the result. And I think that it's a little, if you go too far, it's a little unethical. If I cannot model sidechain, it means also that I cannot really model main chain. So I just remove entire residue, which I know some people would disagree too. I will show in my example why I'm doing it. I'm not doing this randomly. So it's not like I will remove something between two residues which are well modeled. Then if two are well modeled, the one in between, I know where it is as well. Anyway, my opinion about sidechains. So the summary. Basically, almost any low-resolution model building requires manual curation. You should use chemical and evolutionary knowledge, strong or even stronger restraints. And what I use for validation? I use for validation, obviously, agreement between the map and residues, local. Chemical plausibility. So basically, I don't like interactions which cannot happen, and I'm going to rebuild model in such a way that all interactions which I see are reasonable. And yes, include sidechains probably in non-clashing conformations. And now we are going to move to the example. Oh, not yet. Wishes for the software developers. So making reconstruction from the first frames is not easy. So if anyone here develops the software for making the reconstructions, that would be very helpful to have the ability to make this reconstruction pretty much with one button press. Another thing, which is actually not my idea, but my colleague Zbyszek Otwinowski's idea, is that we use TLS in refinement in X-ray crystallography, and obviously we can use it in the refinement in cryo-EM. If the TLS is used properly, it probably would define very well the places where focused classification should happen. So I basically don't use, I use ServoCAD, so I could basically use it that way, but I don't know how well it is implemented in Phoenix. Regardless how well it is implemented, if you are a user and you are using TLS in the refinement of cryo-EM structures, then the TLS bodies can tell you where the focus classification should happen. So now our example. Our example will be published structure of ARM-C just recently. And we solved the structure to two resolutions, 2.75 angstrom for the APO structure. And in case of UDP, we were restricted by the number, basically not enough particles. So we had only 3.8 angstroms, but nevertheless, we built inside the ligand. So now I'm going to stop sharing before and maybe answer some questions if there are any. Okay, let's see. Okay, where is the cryo-EM scattering factor for P relative to C and O? Lower. No, it will not be lower. I wish I would put it together. There is dependence on atomic number. It's just not the same like in case of X-ray crystallography. So basically it will be better visible. Just remember that both sulfur and phosphate is also prone to the radiation damage, and radiation damage will look different in the DNA RNA, where phosphate is actually in the wire of DNA, and it will look differently in the phosphate which is free, for instance, in ATP bound to the enzyme. Then how do you extract those earlier frames? For picking, you want as much constraints, but you could use the total frames to pick the extract. So this is actually usually done differently. First person who actually published zero-dose extrapolation, I believe, is Chris Russo. So what you do first is the full reconstruction. And after you have full reconstruction, full model, you can actually use the first frame. Basically, you go back and just select from each movie only first frame. So what I'm trying to say is that this is not easy. There are no tools which make, unless I'm unaware, which make it easy. So, but I would like to see those tools, because I think that for many, there is absolutely mathematically reasonable to do the weighting the way like it's currently done. You could do this a little better, but this is not equivalent to recovering the signal from the first frame or to zero dose extrapolation. So there is benefit of making it as easy for users as possible. Will it increase your resolution? For most structures, basically it will not make from 5 angstroms 1 angstrom or from 4 angstroms 3 angstroms. But for many particularly weird cases, it may help. So anyway, I wish it would be easier. So now I see that Paul is here. Unfortunately, I'm going to share the old version of the code. So if anyone has questions, just ask, because the sharing will, again, for that, I have to share full screen. And the reason is that otherwise the code you wouldn't see some windows. So let's actually go back. Okay, escape. Okay, let's try again. Okay, finally. So now share again, and we are sharing my entire screen. Let's hope. So I already prepared everything. First of all, do you see my screen? Could someone confirm?
Yes, we do.
Okay, great. So this is AMC, actually the lower resolution, I believe. Let's see. Actually, this is the high resolution. We'll see. Okay. Okay. So first we are seeing this 2.75 angstrom structure. We see the old code. We basically see this is actually the beginning of refinement. You don't see the final refined structure, because I wanted to show you what happens if you dock the AlphaFold model. So as you can see, the AlphaFold model fits quite well. And how do I know? Let's actually first open. Map is completely unsharpened at this point. So the first thing which I'm going to do is open the modules, CryoEM, because there is module in code CryoEM. And I'm going to sharpen this map. So there is a lot of questions about sharpening as well. I actually like to work on unsharpened maps if possible. And there is very weird reason. So sharpening, as you all know, increases the noise. So for missing fragments like this loop, I don't have here, let's see how many amino acids, many. Otherwise I would build it. So this is 213, and this is, not 128. This is my click, 204. So I'm missing about 10 amino acids. 10 amino acids is long enough that I cannot basically do anything. I can make the contour much lower. This is membrane protein, so we start seeing all other stuff. And you can see that at much lower contour, there is some continuity here. So in this case, I did not feel confident enough to build anything. I just left it. By the way, this is the case where, because I wasn't certain where the main chain is, I didn't build any side chains. So still according to my rules. However, frequently, the gap is smaller than 10 amino acids. If this is 2 or 3 amino acids, unsharpened map helps to basically find the continuity, and then you can sharpen it. But here I'm going to sharpen it. There's a lot of ways to sharpen. I'm going to basically use the way which is probably not sophisticated enough. Let's do, I'm guessing here. If this is 2.75, I'm guessing that, let's say, 25 is probably not enough. Let's do 30. And I'm making additional map. I'm just making it, by the way, I feel comfortable because it's relatively high resolution for me. I actually feel comfortable building at this kind of map. However, I know that many people basically don't, and it's perfectly okay. Of course, it's not contoured correctly. Oh, I sharpened wrong one. That's why. I basically try to make it faster by not doing some things, but now I basically sharpen the other one. Will be very useful when I show you the low resolution model building for the 3.8 angstrom structure. So let's select the correct one. This is the correct and the same behavior. Minus 30. So some people sharpen it. You can do local sharpening also in CUD, which I don't do this here. When I build the model, I actually do it quite often. Okay. So you can see that this sharpening just changed it a lot. There is not that different thing, but it will be useful for our purpose. So as I mentioned, map is perfectly feeling by eye, but that's not true because there are here problems. I'm going to remove this map so you can see better and display it as a C alpha. So you can see better how the protein looks like, and we will focus on the fragment, which basically, remember I mentioned the ends of the helix. That's where I usually expect problems, and in this structure, problems were located there. So how I would start? First, I would actually check. You see that here it doesn't fit to the density that well. In particular, definitely helix is going this direction. I'm going to cheat at the end in a few minutes because I obviously got the model from PDP, which is already rebuilt. But I wanted to show few places where actually you have to. So what I do first is density fit analysis. So this is model 002. It looks terrible, probably because I selected wrong map. Let's actually see. This is the correct map. And let's do density fit for my 02. Looks terrible. I'm going to scale it down because it does not basically, oh, I went too far. Rescale, still not good. Let's do 1. Rescale. Okay, still. So that's kind of normal behavior, but I will go a little higher. And the reason is that I want to see the fragments, which are the worst. Because, oh, here, I wanted the worst, and they are here. Let's see. Oh, no, 2 is better. So this is usually the first step which I do for low resolution model building. And the reason is not necessarily finding just the worst places, but also if my docking or molecular replacement with the AlphaFold 3 didn't work, I get very quick answer where the problem is. So here it looks like all chains are placed correctly, and there are fragments which are not very well ordered. So this is one thing. I hope that everybody is seeing it. If you don't see it, tell me. Then another thing which I do almost immediately is Ramachandran plot. Remember I mentioned that this is just docked, and you see we have outliers. So sometimes you just cannot get rid of the outliers. You try, and there is that one which stays there. However, in this case, these outliers look like, I know that I can remove them. And I usually enjoy very much to find, basically removing outliers which are, in my opinion, the worst, which are somewhere in the middle of nowhere. So let's go to this outlier. Now here in this region, which is not very well ordered. So let's actually try to rebuild this fragment. How I will rebuild? Remember, from my perspective, this is not yet super low resolution. Remember, I mentioned those terrible C termini of the helix. So you see here that there is very nice helix. You see that this side chain, for instance, has probably 2 conformations. But let's focus on the one which has problem with the Ramachandran plot. I'm going to open Ramachandran plot here so we can see it. And I wanted you to see how many Ramachandran outliers we have, 18. There is 4 copies, so with C2 symmetry, so I expect that there will be problem with the, basically, at least in each copy, the same one, so let's say at least 9. So the first thing which I do, I'm changing here for low resolution model building the defaults. The default is not to use torsion restraints and not to use Ramachandran restraints. I'm going to use both. Also, refinement weight is 60, which for low resolution is probably not good. Oh, you see 276, so weight should be. And I actually going to use alpha restraints first because I would like to straighten up this helix. Just to know, basically start from the good point at the end. So I'm going to select this. And now my favorite real space refinement. Let's actually try a longer fragment and see what will happen. Not very happy. So, and obviously you are aware, I should sharpen it probably more. Let's actually see interactions. This residue should probably go somewhere else. So I'm going to let it go. It's not solution, but it's not good. It's not good at all. Why it's not good? You see, I selected as an end of helix this residue, and I should be more adventurous here. I should take the longer fragment. If I take too long, there will be problem too. But you see now, it seems that these things jumped where they're supposed to be. And even my arginine, let's actually see, maybe I should actually send it towards in different direction. Even my arginine is not that bad. Okay, so remember there were 18 problems. Okay, I'm writing. I actually believe that Kut knows better than I do what's going on here. I know exactly that this is C and still red. Let's help it a little. I probably moved wrong. It's not anymore the alpha helix really, so it's the problem. So let's check whether I made it wrong, better or worse. So there was 18, there is 20, I made it definitely worse. So why it is worse when everything is better? That's because I actually did not squeeze it enough. So again, I'm going to the default. There's option more control, and I'm going to help this Ramachandran plot to be right. I hope that Paul is not going to get heart attack. So I don't care about side chains at this point. So I just increase it a little. By the way, there is also here a problem which is related to the fact that there is glycine in this helix and it's breaking it a little. Okay, now I'm going to take a larger fragment and we will see whether this will clean. Ah, it looks so great. Probably didn't help at all. It's possible that I'm still 18, so I'm in the same place, but you know, I have other problems. I definitely generated. So let's go here. So this is the C terminus, which I forced to be alpha helical, but that's not how the end of the helix look like. So I gave you that the two most popular. You can actually check on the Roland's page, basically how it looks like. But I can tell you that what I need to do here is peptide flip. So basically it's now too close to this other oxygen, but after I do refinement and remove the helix, this is very important because it's not alpha helical anymore, but I still keep this stronger restraints on Ramachandran. This should help it a little. I'm going to take shorter fragments. And you see it kind of put it out. This kind of end of the helix that you have oxygen and basically going down, 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 and the end of the helix is going in this direction towards the axis of the helix is actually quite common end. I'm not claiming that the other residues which follow this alanine are not right now, so I will have to fix it too. But right now, basically, I'm keeping it like that, and it should fix. It didn't fix this one. It fixed this one, but it generated the next one. So this leucine basically was a problem. Now we have problems somewhere else. I'm going to actually go through all this 18. So now I jump to the completely different fragment. Remember, I still have the restraints which are not alpha helical. So I'm going to again refine it a little. And this is basically a little better. This is clashing. I'm going to make it like this. So I improved this residue, but I'm pretty sure that I messed up the one nearby. Still 18. Yes, I moved this one, but now we have new one. But I'm not worrying too much. Let's actually see. I'm looking for the fragment where I actually have the peptide flip. There is one very clear peptide flip in this structure. So let's actually go here. This is the same syringes in different side, different chain. So let's see. I'm going to. So in the helices, the side chains are going up and down like that. So I'm going to fix it. Do I want to? It's actually interesting beginning of the helix. This is not classical cup. Let's see. Still 18. Maybe I should squeeze it a little. Let's actually see. Could be that I'm not seeing it correctly. I'm seeing it very correctly. Okay, let's jump to this. Where is my peptide flip? Okay, this is the one. Oh yeah, this is the peptide flip. So you see this glutamine. That's why I'm actually starting from it. Peptide flips are kind of worse. So this glutamine has this very bad Ramachandran plot. And you can see that this is part of the helix, and clearly it's in the middle of the helix. And for whatever reason, AlphaFold generated the model in which this oxygen goes there. So we have option peptide flip. This will remove at least Ramachandran outlier, which I saw. We are removing it, and oh yeah, sure, getting better. So it's very painful, 17 residues. And my guess is that there is peptide flip in another chain too, but we will check. Oh, that's not necessarily, yes. So here, remember, I told you that this is the end of the helix. One of the end of helices, but here we have different one. This residue is not going there. This is also peptide flip. So again, most of the problems happen at the end of in the non-class, I would say non-standard structural elements, which you are aware of, alpha helices and beta strands. So let's see. Here we are. Okay, we are 15. So we actually moved just this one. Probably it was affecting two neighboring residues. I don't know which one was the problem here. This is basically copy of this peptide flip, which we saw in the previous. So remember, this is C2 symmetry. So this probably repeats at least 2 times, but it's homotetramer. So yeah, I messed up this residue. So I'm going to wait a little. Okay. So I'm not going to remove all those peptide flips. I'm going to actually focus on the fragment which was rebuilt at the top of the helices. So I don't want you to basically see me removing 18 Ramachandran outliers. I hope that Kut is waking up. Okay. And because I selected just this residue, I probably messed up that bond. So there is some unhappiness there. Oh no, 13. So that fixed a lot. But let's actually open. So I mentioned that I will be cheating. This is 2.8. So the first cheat which I'm going to do, I'm going to actually put here the PDB model. So fully refined model, I already have it here. And let's actually remove map for clarity. And let's see C alpha and C alpha. So you can actually see where we had to rebuild. So as you can see, most of the model is almost identical, but those problematic residues here, okay, I'm coming to this. Very annoying, I must say, but it's my fault, so I'm not complaining. Okay, let's go here. So this top, which was built by the AlphaFold, so this is AlphaFold structure, which we used for molecular replacement, or molecular docking. And this is what we built at the end. So actually, I'm going to see first whether the map, this model agrees with the map better. So let's see this. And let's go to, there is still some problem. There is still missing loop. There is still a lot of, I don't think that we have the same scale. Okay, we are here. So I'm going to now put the map, and we will be looking at the first and the second model, C alpha, the end. Okay. Okay, both of them look quite terrible. Do I have correct map? I hope so. Okay. Display. Let's actually see alpha. This is correct one, and this is basically deposited. Okay, so let's actually see why we build it that way. Okay, and here, for purpose of our discussion, I'm going to actually remove the sharpened map and focus on unsharpened one. And deposited map is here. And maybe a little higher contour. So what we see here is basically classical sausage-like helix. There is a little interactions, remember the ones from the presentation which I mentioned. And we can inspect how those helices interact with each other. Those 4 helices are coming from 4 different molecules. This is clearly disordered. So why I did model it? And why I did model it in this conformation, not the one which AlphaFold liked. Honestly, to make the interactions more reasonable. So specifically, we have here interactions between hydrophobic and hydrophilic residues such as this arginine, which probably would fit better a little lower. Let me see the pink map. Yeah. And we basically have, do I look at the correct model? I think so. Yep. So basically in the green model, what I clearly see in the green model is a problem at the end of the helix, where the helix is basically, there is register problem. So here you see basically there is one turn, there is another turn, and then a program is building yet another turn when the density indicates that this turn does not have place, but rather we have 310 helix, which frequently happens at the end of the standard alpha helix. And then we have C cap. So to basically fix it, and then to basically accommodate the fact that here there was lost amino acid. So basically it should go a little higher and basically be off by one residue. We have this thing sticking out of the density, and then everything comes back to reasonable agreement. I would say these are 2 hydrophobic residues, which I use as a some kind of anchors, which tells me that register is not that bad. This actually agrees with the density. This is unfortunately common in the low resolution, that if you have this kind of interactions between 2 hydrophobic residues, it looks like one is sticking out. So I am not worried by that. And that also is quite common interactions, not worried either. This basically is expected. Remember this radiation damage, and the problem starts here. So basically between residue 271 and residue, let's say 257, so 15 residues or so, things are not fitting that great. So is it this much better? Basically, we fit a little bit better the lucine. We basically accommodated this weird behavior here. Let me remove the green map, not green map, green model. But honestly, I think that I could do this better as well here. Oh, I'm very curious whether I have the correct model, because it could be that I basically overlapped this on the wrong one. Let's see, basically that we renamed the chains. I cannot believe that this is so poorly fitted. Okay, let's see here. And actually, let's do something interesting. This is the beginning, and now I'm going to use, so I'm going to superpose and use, but no, I'm not going to use specific chain precisely because I don't think that it was working that well. Okay. It could be that my approach of overlapping is not working that well. Sorry about it. So we will focus on the basically literally rebuilding this de novo. I still have a few minutes, so I'm going to open this. Do I want to bring? I want this one. Okay, so I mentioned we are at the chain B. Chain B is fine with me, and I'm basically right now looking on rebuilding this one loop de novo. So I will start from the part which is easier for me, which is the end of the helix, because I think that here the helix in this 259 region finished too early. So you see, basically there is helical, and this is the end of the helix, where I think that we have yet another turn here. What I'm going to do, the first thing is removing this proline, because it will be easier to make the helix without having unnecessary connection. So again, everything looks fine, with exception of this, that I want to, for this protein to be alpha helical. Okay. Yes, it's basically quite unhappy in the sense, let me see whether I didn't miss some registry problems. I'm going to let it out here. Okay, this basically is normal that this lucine is actually in the wrong place. Here we are going to force you. Basically, I did the same thing like before. I added one residue too much. Okay, I'm going to accept it and handle this residue manually. So there's two residues as a matter of fact, because there is this and this one. So I'm not touching this side anymore. Now I'm going to the other side. Remember that these things have to, meet each other. And specifically, I see here a lot of density. And the question is it still helix or not? So you see, there is helix here, and there are many ways to finish such helix. And I think that this basically has, again, one turn more. There is glycine here, which I will remove. It has one turn more, but I'm going to force it to be a little. Okay, it's obviously very unhappy, but that doesn't bother me. I'm going to force it. Go away, go away. Okay, now we are adding one more. Here, go there. Go there, go there, go there. Kind of went there without enthusiasm. So basically I put the residue where I think it is, but I have problem with two others. My approach to it will be to remove it for now. Well, maybe not. Maybe they are not that bad. So I'm going just remove alpha helix to be able to make those two residues to go where I want. Here, better sharpening, more sharpened map would be useful, maybe a little, maybe not. So the question is how to basically take those residues. Okay, I'm going to remove everything, you know. Okay, everything is removed. I have the sequence of other subunits, so I can always very nicely recover it. And I'm going to look at it without the problems which those additional residues cause. So my main problem here is that I don't have enough space for all those residues, which means that there are many ways to approach it, like usually. But the way which I'm going to use, I'm going to squeeze things a little. The glycine which is here is the residue number 262. And here I have 270. So 8 amino acids. So just so you know how many amino acids I see here. Let's say that this would be more squeezed. So I have 1, 2, 3, 4, 5, 6, 7. I don't have 8. So that is actually a little concerning. But so why I'm basically talking about that much? Because depending on how I select the 7 versus 8, I have different register. So I would at all costs would like to avoid registry errors. Because at low resolution, it's very easy to make registry errors. And if you make registry errors, this will basically kill you. So I have two choices. And now I'm going to, do I want to make this helix longer? So I'm going to actually do something, again, which I always do. And I know that Paul would tell me to actually do the modeling using there is loop modeler in code, but I'm going to add those missing amino acids because I want to see how much space they take. So I'm adding, but I don't want side chains yet. So I'm adding like, I think I added 5 and I need 8. There will be a moment when this thing will not be able to add anymore. And right now, let's actually make it a little longer. So I'm going to squeeze it. That was a big mistake. Okay. Okay, we are about, do we have all the residues? This is 270. This is 271. Okay. It looks like we have everything. So Paul, feel free to tell me that I'm doing this wrong, because honestly speaking, this loop is actually quite annoying. Okay, everybody quiet, excellent. So there is excellent question, what's happening here? Is it main chain or side chain? Kind of, I don't have enough space for main chain, so maybe it's side chain, but really main chain, we will see. Okay. So here we are, and let's actually try squeeze it a little. I'm very happy, which is not surprising. Okay, a little better. I'm going to try to make it happier. Happier means that those things here become green. So now what I would do next, it's roughly in the density, and just so we clear, it's not good looking at all. So we have more or less correct C-cup. But what I think happens here is that we have one turn of the helix. So I'm going to do this one turn of the helix. And that is why I couldn't squeeze everything, because this one turn of the helix was really not helping me here. Estimate, okay. And this one turn of the helix, if this is the last residue, I believe that this 3 will be the mini helix here. So it happens quite often that you have 310 close to other element. Of course, it's happy here and claims that it's alpha helical liar. I'm going to force you to be 310. And sometimes to force requires you to break. So let's actually make this 310 here. So, as I mentioned, a lot of this is actually painful manual model building. So, okay. So what I meant by one turn, I'm missing side chains, which actually generates the problem here. I'm going to force it to be whatever. So you see here is like the end of the helix, and here we have one turn, 310, which basically leaves the space for one residue because this 310 finished. And now we are going to also play with this one. The reason is that I don't believe that this is basically looking like that. There is no way. Reject will be faster. I think that there is like another turn, and for that to happen, it's better to actually flip it. Okay. By the way, it's again common. This one turn helices happen more often than people expect. I squeeze it a little just to have more space. And now I'm going to remove the restraint for alpha helices and let it straighten up the entire fragment. Okay, still unhappy, but that's fine. I'm going to rotate it any minute. So let's actually see. We're going to. So there are more elegant ways. Again, Qt is very powerful software, and the way I do it is by no means the most reasonable way. I'm going to flip it too. Should I flip this one? Nope. Probably this one. This one is actually correct. We will basically force it any minute. I want to connect the missing residue, which is missing here. I don't remember whether we had any proline here. If so, this also generates problems. So now I'm going to force it to estimate, and I'm going to make, let's do 50. So basically there is fight between all those restraints. So if I'm improving one thing, I'm basically, okay, I'm missing one residue, but at least we know now where it is. Okay, so basically it's not there. Let's come on. Okay. And now I'm going to force it again. Remember when I mentioned that it's 8 residues and I was like not certain whether I see everything. Okay, so what's happening here? Oh, you don't want to go. Okay, that's fine. One more residues. Let's see. Yes, there is one more. Oh, that explains a lot. So basically, I'm going to, how to do this? I'm going to add more. Okay.
We have a few more minutes.
Okay, so let me stop sharing, and I want more questions. And in particular, I would like to. Okay, so first I will answer, how did you dock? Oh, yes, I have opinions about that. I actually use CCPM and very old program called MolRep, which is incredibly fast and in my hands works much better than any real space docking. Oh, Paul has opinions. I was hoping for it.
That's what I do. There are two. If you want to do it without a GUI, use MolRep. And if you don't know where the molecule is in the space, MolRep. Otherwise, jiggle fit tool in Qt, and you can use EM placement in future in a month or two when I sorted out the interface. I'm talking to Randy about that off and on these days. Sorry to interrupt.
No, that's actually great. So basically, I'm using MolRep, and I specifically always check at low resolution. Also, MolRep is very good check for handedness. So if you are not certain of handedness, which for the alpha helical proteins is relatively easy to establish, but for the beta-stranded proteins, not always. So,
well, if you look at Oliver Clark's modeling tutorial, he deliberately chooses an example which has
handedness, yeah. So, the MolRep basically will not solve the structure if the handedness is incorrect. So it happened more than once, unfortunately. So yeah, so that's what I'm using. Do you use CBLAM outliers for finding problems? Absolutely. I actually didn't show you, but the next step would be to put it in ServalCAD, generate a difference map, and actually run MolProBT. And basically those outliers would basically guide me. But could actually very nicely with this green balls shows where the problems are. So, so that's another thing. The problem is that after you run refinement, yes, Paul.
If I may briefly interrupt, there is a Qt plugin that runs Kablam for you. I'm not sure if it's in your version, but
yes, it is. It is. I didn't run it because I wanted to show like a really nasty loop, which I think I modeled now a little better than what we deposited in PDP, but yeah. So the next question is how come...
yes, can I keep interrupting?
Yes, of course.
And secondly, it's my experience, although Kablam is from time to time interesting in its results, in my hands at least, it's there are many false positives.
Yes. So basically, that's the problem with low resolution. At low resolution, I really believe that even unless there is really strong indication that there is a problem with the modeling, you just have to go with the geometry. But yeah, at higher resolution, it could be that there is interesting. Basically, I know proteins which have the peptide bonds which are non-standard. So anyway, so we have also the questions about aromatics which do not lie inside the electron density. It's actually a very interesting question. So a lot of aromatics, particularly if they are exposed, remember this is membrane protein, they actually have a lot of freedom. So what happens is you see C-beta and the aromatics, unless something anchors it with interaction, can be everywhere. So I would say that in transmembrane proteins where there is no hydrophobic interaction, which would actually keep it in the one conformation, it's not that uncommon. So what I do in such situation, I actually put it in the most common conformation, which is non-clashing. So I'm not going to remove it because that would basically mess up any type of modeling. Also remember that very often membrane proteins, which I get out, actually not myself, basically which we get, they are already not in the environment which they would be otherwise. So whether it's amphipol, whether it's detergent, this aromatic residue could be fixed in the membrane, but it's out of the membrane, so it's not happening anymore. more questions. I'm really ready to express opinions. So
Well, can I would the thing is I'm here and I got my camera on. It's very reassuring that when you don't know what the sequence is and you're trying to apply a sequence to a particular polyalanine residue range, it's very reassuring when that phenylaniline goes into a blob of density, and that's very encouraging, and even more so for tryptophans. But they occur, at least in my experience, less frequently. So that's my contrary observation that doesn't lie completely aligned with what you were saying there. I mean, it's not.
Oh yeah, and actually, let me actually share it. I know what you are saying, but it happens sometimes that basically they are not. So let me actually show what you are talking about. Okay, we are actually showing now. I hope that this is right. Good. Okay, so you see this one? This one is perfectly lying in the density.
We don't see anything.
I don't see yet.
Okay, let's wait. I'm already. So do you see it now? No.
Yes.
Okay. So this basically it is in the density. But you know what you are asking, why the density is not that beautifully isolated like it is for high resolution structures. That's unfortunately the feature of the low resolution structures, that sometimes you just don't have such a, let me actually keep the pink one, which is a little more sharpened. So, you know, the interaction is here. In fact, I think that this phenylalanine may be sometimes here too, but I didn't put it there. If you go to the next one, which I definitely use, it's absolutely here too. In fact, could be a little rotated. Remember that this is not the final model. Let's see whether, no, here I put it in even worse. Okay, this blue one seems to be a little more oriented. There is another here. So the blue is what we deposited. Actually, here we see something which, again, encouraging. I'm going to wait. So you see the original AlphaFold model, send it here. We moved it to the blue, basically to the density. By the way, there is another conformation here, but the resolution is a little too low to actually do this type of. So unfortunately, the tip of this helix, which is a little more disordered, the one which I modeled, also have the aromatics. And, you know, could be that this aromatics interact. So tryptophan is considered very aromatic. However, it still has nitrogen. So it could be that this nitrogen is interacting with something which is missing. Anyway, basically, unfortunately, disorder happens and you have choice, model or not model. I try to model as much as possible. So, yes. More questions?
I have a question for you. So if you go back to the maps you showed us earlier, highlighting the radiation damage, so
Yes.
I found those extrapolated the collection strategy very interesting. And would you please give us some more details about what the total dose per number of frame was, and if you have any recommendation for what
I mean, I'm scared to give recommendations, but I have opinions. Okay, let's actually go to the presentation, which I'm pretty sure I have here somewhere. Okay, let's actually see. That's the presentation from current slide, and we will go. I know that it takes a little. Okay, let's see. Okay, it's here. So basically, it's discussion. So I have opinions, and these are really opinions. Some things I know for sure, and some things I have opinions. So I really would welcome other people to basically contribute. So I have opinion about how much you should expose. And specifically, I would like to expose to basically to apply higher doses than more people. And the reason is precisely radiation damage. So when the radiation damage, where you are at this dose, which is about 40 electrons per angstrom squared, there is nothing in the structure. The structure is baked. But for whatever reason, basically the signal for this low resolution baked object increases. So in the current weighting scheme, I don't know whether it's basically weighting scheme or whether it's chemistry of radiation damage, in the current weighting scheme, let's put it that way, it's easier to do 2D classification if you expose a little more. I'm not claiming that it works for every protein, but for smaller proteins, we see the trend that it's better to be a little more like exposing. And weighting scheme is good enough that this does not contaminate your final reconstruction. But then there is also the strategy how to slice. With Falcon 4, you basically get slicing, which is so thin that you can do whatever you want. But with the K3, I really believe that everybody needs to be very careful. And I'm going to prop myself here with Takanori Nakane's recommendations. He recommends 0.6 electron per angstrom square. So 0.7 is very close to what he recommends. And the problem here is that if you go too low, because I worry that some people will go too low, you will actually have problems recovering the structure. So 0.6 seems to be like the original paper by Russo, I think, used around that dose. But then there is another component, which is kind of unfortunate, which is this not very well explained movement at the first 2-3 frames. So basically we know that this is probably because there is differential response of the water and material on the grid and so on. And if you use these very, very small holes, everything works better. But no one wants to use them because you get less data, or basically you have to learn how to do this. So in our hands, it's not always moving. So we don't understand entirely why sometimes it moves, why sometimes it's not moving. I would say that we quite often get no movement on the first frame. If you get movement on the first frame, but second is fine, it's still okay to recover the second frame.
What do you mean by that? No movement on the first one, but the second one is fine. I'm not
sorry,
sure.
You get movement on the first one and second one is. So when you actually, then there is another behavior.
Well, the second one, at least in my understanding of this, is that the particle movement is modeled, right? And what you're saying is that in the first frame between frame 0 and frame 1, or 1 and 2, depends how you number it, that is anomalous in that it doesn't fit the model. Right. Okay.
In some data sets, it's not. So, but then there is another thing. Yes, go ahead.
Well, okay. So I'm unfamiliar with that observation.
I know.
Okay, so is that well established in the field? And if it is the case, don't you have to be very careful about your particle movement and dose if you're collecting such a data set?
You have to be very careful. Actually, very thin dose slicing provides this additional advantage that you can model the movement better. So, there is people do not realize, because we take the tools for granted, but modeling of the alignment of the movies still can be improved. So there is absolutely no doubt in my mind that you can do this better. But it's actually costly operation. These are difficult algorithms, and the current ones work quite well. So there is always question how much effort you want to put in something which works well enough. so I'm not forcing people to actually go and rewrite all the good tools. It's more like I would like to have possibility to get the reconstruction easier from those first frames, or have choices. So I'm showing here the best example. It's our benchmark. It always behaves very well. However, in the non-benchmark examples where we had a little more movement, lower resolution, sometimes we actually average the first 2 or 3 frames to get the map. So, or discarded the first frame and used only second and third, for instance. So there is basically mix and match is actually a very good approach in this case. So I see here the question for maps at 3.5 angstroms, do we have leaf side change occupancy? No, we don't change occupancy to 0. I have strong opinions. We keep 1 and basically let them be.
I agree.
They shouldn't worsen the statistics. So this basically they are weighted too, not in every program, but they should be weighted too. So, keep them with occupancy 1, not to confuse programs. So if there is occupancy 0, you kind of say that you don't believe that they are there, and we know that they are there. Is it not normal to exclude several first frames? No, basically we keep those first frames. Or precisely speaking, the programs which actually weight the data, they weight each frame so that final micrograph which you get has the data with a lower radiation damage upweighted and the further frames downweighted in terms of contribution to the signal to noise. Okay.
So Dominika, to keep this going a little bit, was this data collected on carbon or gold? And
this was collected actually on the standard copper copper quantifoil grid. There was no support, and actually this data behave well. But I can tell you that one thing which absolutely I don't advise to do, but this was 2017, so we were doing it anyway. This was Talos, and we were making the beam really large. And I think that the fact that beam was larger than the hole contributed to the fact that there was no movement. But you know how it is. I don't have systematic studies, and my feelings not necessarily have to be true. So also there was very high density of particles, and we know that high density of particles stabilize the ice. So there's like additional components. So here,
yeah, I think Chris Russo has recently discussed how the size of the beam relative to the hole has some pretty serious impacts here. So
yeah.
you're not alone in your opinions.
But first of all, he probably did systematic studies, which I never do. But then he also, there is like, so I know that some people which I work with are here participating. So basically, I collect still 1 image per hole, and I am considered absolutely insane because everybody else does care about movement. They collect 3 per hole at least, if not 6. So so you lose a lot of data if you try to optimize movement, and perhaps this is not the best strategy. Actually, probably it's not good strategy for most of the projects. If you can win by just collecting a lot of data for many projects. So someone also asked, I often get problem with handcrafted loops after minimizing in Phoenix. Serval cut with outliers. Do you tweak the map weight in Phoenix serval cut? Yes, I squeeze everything for low resolution. I basically can tell you I know that Pavel probably will not agree, but I do not consider z-score -3 bad score or -6 or I don't know what is the lowest observed. Because I really believe that at low resolution, you have to squeeze geometry. And if you squeeze geometry, the z-score will be low. So Phoenix is a little better, but in case of serval cut, I routinely, for the sub 4 angstrom structures, I have to change the weights to be more squeezed. So basically more into geometry.
One cannot, at the least as far as I know, and maybe you've done something of which I am unaware, at least at the moment in serval cut, you can't apply restraints that optimize the Ramachandran plot. Are you suggesting that that's what you actually do?
So I can tell you what I do. I don't know, it works. So there is this thing which you can generate external restraints when you actually put like mini libraries. Yes, for let's say, I will use the example which Ira is aware of, magnesium. So we basically had magnesium at low resolution, and this magnesium definitely didn't want to stay in the place where it's supposed to be with all the attached waters. So we created the file using this ProSmart or something like that and read it externally where every bond was defined with the basically, you know,
Bond
all
lengths,
the
yeah.
sigmas
Yeah.
and so on. So that way I could restrain it locally. Globally, I honestly didn't try that much. Tried, but maybe this is why at the end we always go to Phoenix because
Maybe.
because you know, if it, so I prefer serval cut for many reasons, including, you know, the fact that I'm familiar with everything. But truth is that at the end we always run Phoenix to make the geometry perfect. And what you explained that I cannot actually, I probably tried, it didn't work. So, you know, thank you for that. And I'm sure that everybody who is on the call will be very happy to know that you can change the number in the interface, but it doesn't matter. I'm going to tell something, Garib, about it. Okay.
Well,
Yes.
okay. So me and Lucrezia may have something in the bag by the next time we meet.
Okay, so now I will go to the next slide to actually discuss this. So I on purpose showed this slide because I think that there are several people on the call who actually are trying to analyze enzymes. And in case of enzymes, you really need to be aware of the carboxylation and the fact that things are moving around. I wouldn't say like dramatically. Let me actually find my other presentations, but sometimes the movement is dramatic. And if you analyze the active site where you have, let's say, metal, carboxylic acid, maybe ATP or something like that, you definitely cannot trust the bond lengths at that 2.5, 3.5 resolution. You see the structure, you basically can design mutations, but I really genuinely think that because it's so easy to damage the entire structure, it should be like treated with a little of the, yeah, basically not that much. So I will show you more examples, which we basically shown. Let me see, I have it actually. Okay. Okay, let's actually do escape. And we see. So, okay. Yes, it's a very old poster from one of the 3DM meetings which I attended. And basically for that meeting, we did very careful reanalysis of some of the, let me actually do, so I'm going to zoom. So basically there is method which allows you to look a little deeper into radiation damage, but I'm going to basically focus on one of the proteasomes, which basically this is the 10 to 18 empire. So here is the same thing. In this proteasome, this is absolutely caused by the loss of hydrogen bonds. You have movement of entire helix. So again, movement. It's not necessarily movement because what we observe is actually how the charge changed. So we basically see this, I say that this is movement, but basically those residues should be a little more to the right, or were a little more to the right at the beginning, and our model should reflect this. In fact, we see also an isotropic change movement of the domains. So here is this proteasome subunit, and you see that there is a lot of more green on the top versus basically top right versus the bottom. So, you know, I did a few squeezes here to actually show how it looks like. And basically a little of the composition. Let me see whether we have more features. So here is another view of similar behavior. I'm going to make it even larger. So that's basically different view of the same residues which were before. So this decarboxylation, this is, by the way, quite common and observed in crystallography too. This decarboxylation most likely caused after hydrogen bond was basically broken, allowed this residue to basically change. And it doesn't mean that it moved, but it was enough to basically look like it moved. And there is hydrogen bond here, which basically means that after this hydrogen bond was broken, this started doing something this also was displaced. This is really surprisingly common. So if you interpret something which involves the carboxylation, I would really try to recover the signal. Let me actually see any more questions. Okay, no more questions. So